Welcome back. In this part of the tutorial, we're going to clean this network to actually generate guide curves for our walking paths later on. So right now we have a rough idea of where the paths are going to be, but we need to get rid of all the noise in the data. So one way to start with this is quite easily by just smoothing. Note that smoothing on open geometry actually works differently than on closed geometry. Yes, I should demonstrate that. So if you have a grid like this, you smooth that, probably won't see any difference because it's already relaxed. If you would use a mountain first, you would see the difference. And now if you would smooth, it would smooth like this. It would also try to maintain the same distance between for all the edges. But instead, if you would use the end sub to unroll, and if you would fuse, not fur, fuse that, I guess it shouldn't. It does, yeah. So fuse it back and smooth that. You actually get sort of the same logic as what you had with the older smooth sub before OpenCL. This becomes especially interesting if you actually have a longer curve. But in the case of a grid, we can actually smooth everything to one point, which is what we're going to do with the other thing. So quickly to just be complete. So if I would use just this, by default it will actually pin a group boundary. You can actually smooth curves as well as closed primitives. Okay, so let's do that. Get rid of this. Go back to showing everything again using G. And now we can just increase the strength to quite a high number. Although maybe 10 is already enough. Yeah, okay. Because we don't want to lose too much of the curve definition. So let's keep it at 10 for now. Okay, so right now we actually have like really dense areas and kind of sparse areas. So we're going to use that to our benefit with a wrangle. And what I'm going to do is delete all the points that are in low density areas. So if the length of the array of all the nearby points, which you can get using near points, from the first input around the curve position, we did a range is smaller than a number, we remove that point. Okay, we can again click this button to generate our parameters. So we want to check within a range of 2. And we want to say remove everything. Yeah. So this is maybe a bit too aggressive. So maybe we can increase our range a little bit. Yeah, that's too much. Okay, let's tweak how many we want to keep. Yeah, okay, I'm happy with this, but feel free to tweak this to your own liking. But in general, we probably have easily enough paths in the end anyway. So we still need to remove a lot more. So let's add a fuse sub. We'll set it to snap. And we set the distance to 5. This will immediately clean our results or make it quite more readable. But right now the actual geometry is still quite dirty because all the primitives still overlap. Just to make sure that all the points that snap to each other within 5 meters are not nearer than 5 meters to one of the other snap points. I'm just going to repeat the same process. Let me, not sure where it was again. But I think actually it mentioned somewhere in the help file of the fuse sub. It's a good reason, good idea to do this. I want to waste too many times. Too many times. Okay. I don't think. No, I can't see it. But basically, because every point only looks at all the surrounding points, it doesn't take into account the results of the process. Much like something in a wrangle node. So if you want to a point to actually process over the results of all the other points, you'll probably have to process the code in a loop. But here we just do it 2 times, snap 2 times. So now we're just gonna fuse again. This time we'll keep it on consolidate, just to make sure that we get rid of all the overlapping points, and also to get rid of the floating points. So now we can also start to get rid of all the overlapping primitives using a polypath. No, not polypatch. Polypath. we go. And to reduce the amount of paths again, I'm going to create a wrangle node to group all the intersections. So I'm simply going to say group underscore intersections equals neighbor neighbor counts of the current points is not equal to 2. So this will basically group all the intersections as well as the endpoints. So I'm just going to so this is nav. Okay, I'm going to copy paste these, and now you should be able to see the intersections group. I'm going to use that in this use sub as well as this one. By this one, it doesn't really matter too much. But now we're going to increase the range in this snap, because if we give it a 5, there shouldn't be, well, apparently there is still difference. But I think we can safely put it at 10 to just reduce the amount of intersections that we get next to other intersections, basically, so we don't create a lot of roundabouts in our paths. We fuse again. Right now, what I'm going to do is only keep one segment between every intersection. So to do that, I'm just going to remove all the points that actually have 2 neighbors. If neighbor count of the current number is equal to 2, remove points. Okay. And just to check, yeah. Right now you can still see that there's sometimes overlap, because there's 2 paths between 2 intersection points, and that's basically what this solves if we use a polypath again, because that will basically generate one edge between every intersection, or continuous edge if you have more or than one edge points on the edge, like we had here, for instance. Okay, so because of examples like this, we still have edges where we actually have this happening. So I'm just going to do the same again. Oh no, just going to copy paste this to get rid of those. Okay, and now we actually start to get more clean networks. But right now we still have way too many paths. So we need to do a lot more cleaning still. One easy type of path that we want to get rid of are things like these, which is just one path with two open ends. So we can do that, and we can loop over primitives, and we can just check if the last and first primitive both have one neighbor. So let's create an array of all the points, which should be only 2 points. Because we removed all the points in between the edge, which is apparently, yeah, it is true, but yeah, because we still didn't do another polypath after this. But basically, you could keep doing this basically in a loop as well. But for now, I'm just going to do it only 2 times. So the current primitive, and now I'm just going to check the neighbor count of the first primitive, the first point in the primitive. If that is 1, and the second primitive, or the last one. You could also say -1 in this case. -1 actually works to pick the first index from the end of the array. This is a feature they added in, I think, Houdini 14, basically making arrays in VEX much more like Python in terms of slicing, I think it's called. So if both points are open or only have one connection, then remove the primitive, and all the points on the primitive. Okay, check. Yeah, so this example should get removed. There we go. Okay, so now we need to do some kind of process to reduce the amount of paths that we have much further. So for instance, what we could do is simply remove all the short edges. So let's do that. Let's measure the edge. Actually, I'm going to reduce the window here, because we will go through a couple of iterations to do this. So the most simple version would be if the perimeter is smaller than a threshold, remove the primitive. And also the points. In this case, we want to run this over primitives. Okay, so if I generate the parameter and I start cranking up this value, we want to have a larger range in this case, say 50. Yeah, so you can see that it starts removing connections. But this is a bit too dumb. So for instance, what we could do is only remove edges that are already on the end of a grid. So let's copy paste that. And we could do that using the same technique that we did here. So also this. So if one of the edges is not equal to 1, we want to skip this code. So now if I do return, yeah, now it only removes curves on the edge. So why does this work? Basically, per primitive, I'm checking the neighbor counts of all the points. And if either of them is 1, I execute the code. And if none of them is equal to 1, I skip the code. Okay, so that's the start. But now, yeah, you can see, I think in this case, yeah, that because we started to remove edges like this now becomes one curve without any intersections in between. And we can imagine that if we keep repeating this step, there would be new cases generated with every step where stuff like this happens. So because it's an iterative process, we probably want to do this process inside a loop. So I'm going to copy paste this again. Create a for each loop with feedback, or a for each number if you're running this in the 16 instead of 16.5. And in that case, you want to do it by count and set this to feedback each iteration. And I'm just going to set it to 1 iteration at first. Okay. And in this case, we actually want to get make sure that the system actually knows that this is a single connection. So what I'm going to do is add a polypath. Again, we will use this node quite often. So yeah, you can see that now it generated 1 primitive between every connection again. And after that, I actually, not this one, yeah, this one. Remove 2 neighbor points. I'm just gonna paste this, put that there. So basically it will remove the corner points again. Okay. So now we should be able, yeah. Okay, yeah. So here's like a case where we start with a branching structure that gets shortened. And if we would run this multiple times, it should actually remove this as well. I guess maybe because it's not long enough. Yeah, there we go. So now you can see how this works. It's an iterative process. Yeah. But I think we want to keep this at a reasonable number. Okay, so this is the first real iteration of our cleaning algorithm. Let's enhance it. So I'm just going to copy paste it. And I'm going to actually, instead of removing the edges, I'm actually going to group them. So yes, and in this case, we don't really care about if it's an endpoint or not. So group collapsible equals perimeter is smaller than the threshold. Okay, then we need to add a group promote and go from a primitive group to an edge group and select collapsible. There we go. Yeah. Okay. Then we add a edge collapse and we inject this group. Yeah, so basically that makes it way too aggressive. So I was actually mistaken and probably want to keep this logic. Yes, okay. How does this relate? Yes, okay. One thing we probably want to do is actually delete the group afterwards as well, because otherwise it might actually affect the next iteration. Okay. I'm just going to select all of these, hold the A key, and drag downwards to align. Let me double check. No. Oh yeah. This is a quirk of the for loops is that sometimes you actually have to put the render flag on the end first to update the algorithm inside as well. So why is this? Ah, yes, we only want to include the elements contained in the original group. That's my mistake. Okay. So now if we start really increasing the iterations, we start to see let's compare between this and this. Still quite similar, except in this case, it's sort of averaged the position instead of removing the entire edge. So in that case, it sort of better maintains. Yeah, you can see basically the difference. So it sort of better maintains the average direction of the curves. Okay. So yeah, what you can actually see is that it doesn't really change a lot over the iterations. So one thing we can actually do is copy paste this again. Click on this node and create a meta import node. If we middle mouse button click on it, we can see the detail attributes that are generated, which is inter iteration, I value, num iteration, and value. And we will connect that to this wrangle, which will be group collapsible strings non-ends. Okay. So what do these values do? Basically, they show which iteration of the loop it currently is on. So if you specify here that the start value is 1, then I value will be 1 in the first iteration, and the actual iteration will be 0, because programmers start to like to start to count at 0. So if I would set start value to 0, you would see that I value is also 0, and num iterations is this value, and value is like just the I value is the integer version of this value, basically. I'm not exactly sure why this was added, but you could also have a float version of the iteration if you wish. But in our case, we actually just want to start at 1 because we're going to use this in math. Okay, so what we're going to do is actually create a custom threshold. So float threshold equals this threshold, and this threshold will go there. But the interesting thing is that we're going to multiply it with the value that we generate in the metadata. Value. So that means that every time we go through the loop, and if we increase the amount of iterations, that the I value will increase as well. So every time, every next iteration, the threshold will become larger and larger. So the amount of edges that it will collapse can become larger and larger as well. So ideally, that should now make that if we increase the amount of iterations, that it will start to remove more and more edges. but apparently there's still like a limit. Ah, yes, because eventually it will find all the endpoints and it will stop. Yeah, okay, so that seems okay. Let's say 10. And let's copy paste this here just to see how that would work. Yeah, I don't think that actually does anything here. No. Okay. So we'll go one iteration further. But I think I'll show that in the next version, the next part of the tutorial. So hope to see you there.